Okay, so the next is conversion. Metric prefixes expressed as powers of 10. So we have here, example, express 2.1 volts in millivolts. So volt is bigger than millivolts. So that means to say, since volt is bigger than millivolts, so if we're going to convert volts to millivolts, expect that the number will become higher than 2.1 since volt is higher than millivolts. So milli is, that is 10 raised to 10 raised 10 to the third power or 10 cube, because 1 milli is 0. If you will observe here, milli, the equivalent of milli is 0.001. 0.001. So 1 divided by 0.001, it's 1,000. So that's why 1 volt is equals to 10 cube. So if we're going to convert now 2.1, just like what I said, the expected answer, the number should be greater than 2.1, although they're just the same. The two are just the same. The only difference is when it comes to the unit. But 2.1 volts is equal to 2,100 millivolts. So what I'm just trying to say here is, since volt is greater than millivolts, so meaning that the number expect that the number expected here is bigger than 2.1. But again, do not be confused. 2.1 volts is just the same with 2,100 millivolts. So again, why it's 10 cube? Because 1 volt divided by, when we say the equivalent of milli is 0.001, as you can see here on our table. So if 1 volts divided by 0.001, we will arrive at 10 cubes. So 2.1 times 10 cubes, that's why we have here 2,100 millivolts. So here it's 0. Express 0.006 ampere in milliamperes. So same with sample A. Ampere is bigger than milliamperes. We're talking here of the unit. So expect that the converted number will become higher than the given. Okay, although 0.006 amperes just the same, is just equal to 6 milliamperes. Okay, so milli, again, it's 0.001, so 1 divided, so that's why we have here 10 cube. So multiply it to 10 cube, then that's why we have 6 milliamperes. Again, 3, we'll just have to count 3 places to the right. So 1, 2, 3, so that's why it's 6 milliamperes. So here, change 356 millivolts to volts. So this time, expect that since millivolts is lower than volts, so expect that the converted number or the converted decimal will be lower than 356. So that's why it's -3 here. So we have 356 times 10 -3. So that's why from here, here is you can now apply the power of 10 conversion. So the decimal point here is here. Decimal point is in this place. So 1, 2, 3. So that's why it's 0.356 volts. So here, another example, change 500 1000 ohms to mega ohms. So equivalent is 10 to the negative 6. So it's 500 ohms. So you just have to move 6 places to the left. So 1, 2, 3, 4, 5, 6. That's why it's 0.5. So we will be doing the same step here in sample letter E. It's picofarad into farads. So since farad is bigger than picofarad, so expected the number that the answer is that the decimal number is lower than the given. So 1 picofarad is equal to 10 to the negative 12 farad. So we have here 20,000. So you just have to count 12 from the decimal point. So it's here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 4 more zeros. That's why it's 0.00002 farad. Okay, so let's have the scientific notation. So the coefficient of the power of 10 is always expressed with 1 decimal place and the required power of 10. So again, when we say scientific notation, it is expected that it will always be expressed with 1 decimal place. Okay, 1 decimal place. Like for example, here we have 300,000. So 1 decimal place, so that's 3. So only 3. So the next thing that you're going to do now is to count since we only need 1 decimal place, so it's 3. So it's 3. So the decimal point is here. So let's now count let's now move the decimal to the right. Okay, so 1, 2, 3, 4, 5. So we have here, so that's why it's 3 times 10 to the 5th power. So here it's 871. So 1 decimal place, so it will become 8.71. So let's count how many places and up to 1, 1, 2, so it's 2. So here, 1 decimal place again, so it's 7.425. So from here, let's count 1, 2, 3. So that's why it's 3. Now here, how about here? It's 0.001. So 1 decimal place, so that's why it's 1. So from 1, it's here. So from the places, how many? So it's 1, 1, 2, 3. So it's negative 3. So here it's 1.5. So the decimal point is here. So from here, between 1 and 5, so decimal point will be here now between 1 and 5. So from here, so it's 1, 2. So that's why it's negative 2. Okay, so again, scientific notation, it requires you to express the power of 10 with 1 decimal place. Okay, rounding off numbers. How about rounding off numbers? A number is rounded off by dropping 1 or more digits at its right. If the digit to be dropped is less than 5, we leave the digit as it is. Again, if the digit to be dropped is less than 5, well, you know that we leave the digit as it is. Like for example, 4.1632 rounded to 4 digits. Rounded to 4 digits, so 1, 2, 3, 4. So since the last is 2, so it will remain as is. So it will, so since the number is less than 5, the last number after 4 digit, after the fourth digit is less than 5. So we leave the digit as it is. So that's why it's 4.163. So rounded to the 3 digits, so it's 1, 2, 3. So since the next number after the third digit is less than 5, so again, the rule, we leave the digit as it is. So if the digit to be dropped is greater than 5, we increase the digit to its left by 1. Okay, so here, for example, we have 7.3468 rounded to 4 digits. So 1, 2, 3, 4. Since the fourth, after the fourth digit, which is 6, is bigger than 5, so we add 1. So instead of just putting 6, we will add 1. So that's why it's 7.37. Rounded to 3 digits, 1, 2, 3. So it's 6. After the third digit, it's 6, which is greater than 5. So that's why we have here, we add another 1. So that's why it's 7.35. If the digit to be dropped is exactly 5, that is 5 followed by nothing but zeros. We increase the digit to its left by 1. So again, take note, if the digit to be dropped is exactly 5, that is 5 followed by nothing but zeros, we increase the digit to its left by 1. If it is an odd number, and we leave the digit to the left as it is an even number. So if maybe some of you already forgot what is odd number is 1, 3, 5. Okay, so again, take note of this. If it is odd number and we leave the digit to the left as it is an even number. So for example, here is 2.175 rounded to 3 digits. 1, 2, 3. So from the rule, from its rule, the digit to be dropped is exactly 5. That is 5 followed by nothing but zeros. So it's 0. Here, there's nothing but zeros. We increase the digit to its left by 1. So that's why it became 2.18. So that's why it becomes 2.18. So rounded to 3 digits, this is 2.185. So instead of 2.19, it will just become still 2.18 because of the rule. If it is odd number, we add 1. Again, add number 1, 3, 5, 7, 9. If it is odd number. But if it is an even number like 2, 4, 6, 8, like for example here it's 8, so we leave it as it is. So that's why it's just 2.18. Okay. So any digit that is needed to define the specific value is said to be significant. Again, when we say significant, any digit that is needed to define the specific value is significant. We refer it as significant. For example, a voltage of 115 volts has 3 significant digits, 1, 1, and 5. When rounding off numbers, 0 is not counted as a significant digit if it appears immediately after the decimal point and is followed by other significant digits, such as zeros, must be retained, and the count of significant digits must begin at first significant digit beyond them. For example, 0.00012 has two significant digits. These are 1 and 2. And the preceding zeros don't count. However, 18.0 has three significant digits. In 18.0, in this case, 0 is significant because it is not followed by other significant digits. So in electricity, specific values are usually expressed in three significant digits. So round off the following numbers, the three significant numbers. So we have here 5.6428. So it will become 5.64. Three significant numbers. So 49.67. So it will become 49.7. So 305.42 will become three significant digits. So 1, 2, 3. So it's 305. So 782.51 equals 783. Okay. So 0.003842. So it will become 0.00384 and so on. Okay. So here's just the same.